Hello, this is a presentation on material science of rocket construction. Introduction. Materials. Materials are an important aspect of engineering because of the unique properties each offer. Examples of these properties are strength, ductility, resilience, etc. The act of modifying materials to attain specific material properties is known as material processing. It is used regularly within all kinds of industries to achieve desired goods and products. The space industry and rockets. For the past decades, technology within the space industry have constantly evolved. Looking back to NASA's Apollo missions from the 20th century, the rocket, Saturn V, was used to get astronauts to the moon so it traveled no further than the moon. Today, NASA is developing a rocket called the Space Launch System that aims to travel to deep space, or space beyond the Earth-Moon system. As the ambition of space exploration increases, so must the capability of the rockets. Material processing plays an important role by developing new materials whose properties withstand much longer exposure to extreme external stimulus while also being efficient in design. This is why we will be looking at rockets throughout the whole presentation as they showcase the importance of material science in engineering. Conditions a rocket must withstand. Throughout a rocket's operation, it must experience various external stimulus, many of which being potentially harmful to its shell and inner parts. Listed here are sources for external stimulus that is most impactful for the rocket. High amplitude vibrational waves. At a rocket's liftoff, the engines must be first ignited to initiate the combustion for the propulsion of a rocket. However, upon doing this, very high amplitude acoustic noise are created and reflected from the ground, enveloping the rocket and causing vibrations throughout the structure that are enough to damage it. Atmospheric drag. As a rocket launches into the sky, it goes against the air, causing a friction known as atmospheric drag. This can produce a considerable amount of force on the rocket depending on the density of air and how fast the rocket is going. Max Q is a critical point during a rocket's flight because it experiences the most atmospheric drag. Extreme temperature. A rocket can also experience a substantial amount of heat. During re-entry, when a rocket must travel back into the Earth's atmosphere, the particles of the atmosphere begin to ionize throughout the front of the rocket, greatly increasing the temperature of that portion. Space radiation. Like anything else, a rocket is prone to radiation, but as it travels into space, it endures higher concentrations of that radiation. Sources of radiation include solar flares from the sun, the Van Allen belt, or two belts that surround Earth due to being trapped by its magnetic field, and galactic cosmic rays that come from the solar system. Tsiolkovsky rocket equation. The rocket equation derived by Tsiolkovsky describes the motion of the rocket-like vehicles. He derived it using the conservation of momentum. It relates the change of velocity from the initial to final state to the exhaust velocity, which is the velocity of the gas leaving the engine's nozzle. That is the product of the ratio of the initial mass, which is the mass of the propellant and the structure combined, and the final mass, which is only the mass of the structure since all the propellant has been used. The main reason this is important to the material selection is that the higher ratio of the initial mass and final mass, the higher the maximum attainable velocity is. Material selection. Important considerations. The three integral factors we need to consider when selecting materials for aerospace applications are materials density, its mechanical properties, and its thermal properties. There are more factors that play a role, but these are generally the most important. Material density. We want the density of the material to be as low as possible, as shown in Tsiolkovsky's rocket equation, since the lower the structural mass is, the greater the rocket's velocity. Mechanical and thermal properties. These two are very important, as not only will a material without the necessary properties to endure the extreme conditions of space would cause catastrophic failure, but materials with the properties that are even better than necessary can allow us to optimize the design of the vehicle, potentially using less material and therefore less overall structural mass. Aluminum. This slide covers the properties of aluminum and its typical alloy. Aluminum has been the standard for all types of flight structures due to its low density while maintaining strength comparable to other metals. It is very cheap and easy to manufacture, costing less than $3 per kilogram. Its main drawback is its low melting point compared to the other options such as steel and carbon composites. Aluminum 2219 is a typical alloy used in aerospace applications. so its data on the right can be used as reference to gauge properties of other materials. Aluminum 2219 and 2014 were used extensively to construct the Saturn V and many other rockets. Aluminum-lithium alloys. Aluminum-lithium alloys are an alternative to the conventional aluminum alloys and can be even considered as an upgrade. It provides an immediate weight reduction of around 7 to 20%, it has an increased modulative elasticity of up to 12%, and increased ultimate tensile strength of up to 20%. Alcoa 2090, a prime example of the potential of aluminum-lithium alloys, was designed specifically for high-strength aerospace applications that reach peak values, as shown on the slide, while having a lower density. They can also utilize many of the fabrication techniques used for typical aluminum alloys to avoid redesign and extra costs. However, they do have a low transverse toughness, so there would need to be considerations for that in some aspect of the redesign. Carbon-carbon composites. Carbon-carbon composites are made up of an amorphous carbon matrix and reinforcing carbon fiber. They are most notably renowned for their unmatched strength to density ratio. Just as noteworthy, however, is its thermal shock resistance, with the ability to retain stable mechanical properties at temperatures approaching even 3000 degrees Celsius. The main mechanical drawback to carbon-carbon composites is its proneness to oxidation. It is susceptible to oxidation at temperatures above 350 degrees Celsius with a rate rising with temperature. This oxidation causes rapid degradation to the material, so it is necessary to have a protective coat. The Space Shuttle orbiter had carbon-carbon tiles, which they layered with silicon carbide, providing protection up to 1200 degrees Celsius. The main processing technique used to make around 90% of the carbon fibers is to make them out of polyacrylonitrile, or PAN for short. The process starts with stabilizing the PAN fibers by first heating it to 250 degrees Celsius range to pick up the oxygen molecules and rearranging its atomic structure. It is then carbonized by being heated to about 1200 degrees Celsius in an oxygenless furnace, which vibrates all of the non-carbon items. It then receives a surface treatment of slight oxidation in order to give it better surface bonding properties. Two options for fabrication are liquid phase infiltration and chemical vapor deposition. For LPI, the fibers are first impregnated with resin petroleum pitch, then pyrolyzed several times. It is then heat treated to 1500 to 3000 degrees Celsius. For CVD, the fibers are infiltrated by a high pressure of hydrocarbon gas at 1000 to 1200 degrees Celsius, and then pyrolyzed and heat treated. These complex fabrication processes drive the price up considerably, costing around $180 per kilogram. The reinforced carbon-carbon panels on the Space Shuttle even costed upwards to $100,000 per square foot to produce. Metal matrix composites. Metal matrix composites are composed of a metal matrix reinforced with other materials. The main reason they're desirable is their ability to tailor the mechanical and physical properties to fit certain needs. However, they are much more costly than typical aluminum alloys, and that certain particulate reinforced alloys have shown poor ductility and toughness in the past. The three primary methods used to form metal matrix composites are high-pressure diffusion bonding, casting, and powder metallurgy. The method mostly used for spacecraft construction has been high-pressure diffusion bonding to form composites such as boron aluminum, graphite aluminum, and graphite magnesium. High pressure in conjunction with high heat is applied to the two metal components, causing microscopic deformation, which leaves the joined regions homogeneous. Graphite aluminum was used to form the high-gain boom antenna on the Hubble Space Telescope for its desirable stiffness and electrical conductivity, and boron aluminum was used to construct the frame and truss members of multiple parts of the Space Shuttle orbiter in the form of tubular struts and provided a weight reduction of 45% as opposed to if typical aluminum alloys were used. Polymer matrix composites. Polymer matrix composites, or PMC for short, are often considered because of their very low density as well as its simple processing methods. They can save anywhere from 25 to 50% in weight, and it is estimated that, in the long run, composites like graphite epoxy may be even cheaper than monolithic metals used in the same application. There are actually three types of PMCs: thermoset, thermoplastic, and rubber, but only thermoset is considered for aerospace applications since thermoplastics form weak bonds, and rubbers, while having some uses, are not used for obvious mechanical and thermal reasons on structural parts. Thermoplastics, on the other hand, form extensive cross-linking and strong covalent bonds, making them better fit for these applications. Graphite epoxy is the main PMC used for primary spacecraft structures, forming propellant tanks due to high thermal stability and also making them good structural truss members. Stainless steel. Despite being very dense, stainless steel is used in various aerospace applications due to being cost efficient while also presenting great properties. Under extreme temperatures, stainless steel even comes close to the strength of carbon composites. Under cryogenic temperatures, many metals, including most steels, become brittle. However, since stainless steel 301 contains high amount of chrome nickel, it allows it to become 50% stronger at this temperature. Stainless steel 301 can handle 800 degrees Celsius before deforming, while also reflecting some radiant heat before absorbing it. Stainless steel can be used as a regenerative heat shield by being actively cooled by a liquid due to being able to sustain high temperatures. It is about $3 per kilogram, making it very cost efficient. The stainless steel would be manufactured by cryogenic forming, which means they are worked at temperatures below 190 degrees Celsius. Benefits of this method include increased uniform elongation at low temperatures as well as up to 70% improvement in failure strain at cryogenic temperatures. Ideal rocket. Propellant tanks. Choosing the right material for propellant tanks of a rocket is extremely important because a lot of the rocket's mass is concentrated there. These parts also bear a great amount of mechanical force during ascent. Historically, the 2000 series aluminum is used for these tanks because they have a strengthening effect when experiencing cryogenic temperatures. Propulsion systems and pipes. The material used for these components must be able to maintain its mechanical properties and endure a substantial amount of heat and cryogenic temperatures, as it carries fuel to various different auxiliary pressurized systems and house combustions. We chose to use stainless steel 301 as its ductility is sufficient to accommodate the necessary curvature of the pipes while also strengthening at cryogenic temperatures. Structure. The main frame and structure of a rocket experiences a lot of mechanical load and external stimulus such as collisions with random space debris and direct heat from the sun. It also makes up a good portion of the rocket, so lightweight material is key. For these reasons, we chose aluminum 2090 for its low density and high yield strength. Heat shield. For the heat shield of the rocket, we went with carbon-carbon composites because of their extremely high thermal shock resistance and their high strength-density ratio. It would need to be coated with a protective layer such as silicon carbide to prevent oxidation from rapid degradation.